Now, what happens if we take our sound waves and we put it in a tube? What if we put it in something that has a fixed barrier? What happens to it? If you're trying to imagine how this could work, well, just blow across whatever water bottle you might happen to have handy. So you might hear it hum pretty loudly. You might have to fiddle a little bit, but you should be able to get it to hum. And that's what we're going to be talking about for the next little bit. What happens is that sound goes into the part of the bottle that's filled with air, and it moves through the air until it hits the water surface or the solid bottom of the water bottle. As the sound wave moves, remember that wave is a wave of compressions and rarefactions in the air pressure. So what happens to the sound when it hits that fixed barrier? I've just hit play now on a simulation. This is from Dan Russell's website. He's in Penn State. It's a super duper website, really great for seeing how things happen. So what I'm showing here is that a wave coming in from the left end traveling to the right, and that wave bounces off the right end. So we have incident waves and we have reflected waves, and those waves interfere just like the waves on a string. And just like the waves on a string, under just the right conditions, you can get standing waves in an air column. That's what happened in that pop bottle when it rang out really loudly. Kind of took me 20 seconds to get it, but eventually you do get it. So now what we're going to do is let's look at the motion of the air molecules that make the standing waves. Let's focus and see what we can say about the motion of those air molecules in the tube. Here I'm playing the Dan Russell simulation again. First, let's just look at the one on the top, and then we'll talk about the one on the bottom. So the first place let's look is over here at the left end. So the air molecules are the little black dots. Sorry, I said left end. I should have said right end. At the right end, what's happening to those air molecules on the right end? They can't move. So at this place right here, they can't move, which means no motion. So this is a node. Okay, so with regards to motion of the air molecules, the far right end is a displacement node. What about other places? So are there any other spots where the molecules aren't moving at all? One of the little molecules is in red, so look at what's happening right here. None of those molecules are moving, and that's not the only place. That's also true right here, and it's true right here. So in all of these places, these are also nodes because the air molecules are not moving at all anywhere along this spot. So node, 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 node. Remember, node we represent with an N. So there's no motion of the air molecule, that's a node. Okay, what's going on in between the nodes? In between the nodes, the molecules are moving a lot. So here's another little red molecule. And if you look at that one closely, you see that that moves a great deal. So in between all of our nodes, there are antinodes. And at these places, we get maximum motion. So a way to represent our standing wave in a column of air is to draw a graph of the displacement of the molecules as a function of time. So places where we have the antinodes, we get the maximum motion in the displacement graph. Places where we have the nodes, those points in the graph don't move at all. So we've talked about the displacement of the air molecules in the tube, how some of the air molecules can move quite a bit and some can't move at all. But a more physically accurate way to think about the standing sound wave would be to think about the pressure wave. So we know there are areas with molecules close together, some spread out and some equal at the equilibrium pressure. So how can we talk about the pressure in the standing sound wave? So let's look at the right end of the wall again. So what's happening over here? If we look at what's happening right here, the air molecules at the very end, they don't move at all, but the neighbors move back and forth an awful lot. Sometimes the molecules at their end are all squished together, and sometimes they're spread out quite a bit. So there's an alternating high and low pressure. That means at our far right end, there is a pressure antinode. So right here, we have a pressure antinode. There are some places in the tube where there's no variation in air pressure at all, and it's always equal to equilibrium pressure. So an example of that would be right about here. So the air molecules shift back and forth, but overall they don't get closer together or spread out. So at this place, at this point, the air molecules are always at equilibrium pressure. So at the node, they're at equilibrium pressure. And at the antinode, they're very different from equilibrium pressure. So what we see when we compare our displacement graph and our pressure graph is that they're completely out of phase. They're completely opposite. Where there's a displacement node, we have a pressure antinode. Where there's a displacement antinode, we have a pressure node. Now, we said that we get standing waves in tubes for certain frequencies. Let's see what the conditions are. So we're talking about standing sound waves, and first we'll look at tubes which are closed at both ends. The first thing we'll do is let's write down what our boundary conditions are. And the boundary conditions are, at the closed end, we have a displacement node. And we have a pressure antinode. So that's our boundary condition at a closed end. We know we can draw the pressure waves in the tube, so let's draw the pressure waves in the tube. So we'll do a pressure picture first. Let's say our tube has length L. Our first picture of a pressure wave, we know we have an antinode at each closed end, so we must have a node in the middle. Our first wave looks like this. So in this wave, we go from a crest down to a trough. We have a half of a wavelength in our tube. So 1/2 of our first wavelength equals L, lambda 1 equals 2L. What about our next wave? Well, our next wave would squeeze in an additional antinode. So we go crest to trough, back to crest. That means for our second picture we draw, the second possible wave, the wavelength is equal to the full length of the tube. Our next picture we can draw, we have to get in one more antinode. So as we draw this guy, we go crest to trough, back to crest, that's a full wavelength, down to another trough. So we have 1.5 wavelengths in our third picture, or 3/2 lambda equals the length of the tube. So lambda is equal to 2/3L. Okay, so there's our picture. Let me just finish that bottom picture. There's our picture, and there's our wavelengths established. If we're looking at the pattern for our wavelengths, we have 2L, just L, which we could also write as 2L/2. Then for our third one, we've got 2L/3. So it looks like our pattern is 2L divided by an integer. What about for our frequencies? Well, the frequency in our first tube is F1 equals V over lambda 1, which is V/2L. The frequency in our second tube, F2, is V over lambda 2, which is V/L, which we could also write as 2V/2L. In our third tube, we've got F3 equals V over lambda 3 equals V/2/3 L, or 3V/2L. Okay, so it looks like our frequencies have a pattern emerging. Our frequencies are V/2L times some integer. Okay, so now we have equations for our wavelength and our frequency. Let's just get a little tiny bit of terminology before we write down our equations. Our first wave in the tube, just like our first wave on a string, is called the fundamental. So our first wave is the fundamental. And then overall, all of the different possible waves and tubes are called the normal modes or the harmonics or the resonances. Sometimes I suppose too they're also called the resonant modes. What else should we write down? Oh yes, V stands for the speed of sound in the medium in the tube. Normally that's going to be air, but it could be other things as well. So speed of sound in medium in tube, usually air. If the air temperature is given, you use the equation we had for speed as a function of temperature. If the speed is not given, you can usually assume that V equals 343. Okay, so we've drawn the pressure waves. We know, of course, also that we can draw waves of displacement, which is how much do the air molecules move around. Let's draw those as well. So for our displacement, we have nodes that are closed in because the air molecules can't move around. So for our first one, we go from an equilibrium to a crest to an equilibrium. We have a half of a wavelength in this tube. So it's the same as the relationship as in the first pressure wave. Our second wave picture, we've got another node in between the two nodes at the end. So we have a full wavelength in this tube. And then in our third, we squeeze in one more node. So we've got one full wavelength and then another half. So 1.5 lambda 3 equals L. So we see that for our displacement picture, the relationships for frequency and wavelength are the same, which is good because we're just using a different picture for the same phenomenon. Okay, let's get a nice definition written down for our waves. So for tubes closed at both ends, the relationships we have are that the wavelength of the nth harmonic is equal to 2L over n, where n is an integer, 1, 2, 3, or 4, called the harmonic number. The frequency of the nth harmonic is n times v over 2L. We see that v over 2L is the fundamental, so we can also say that the frequency of the nth harmonic is n times f1. And n equals 1, 2, 3, so on, is called the harmonic number. Now, there's one more little tidbit that can be really useful when we're talking about tubes closed at ends or open at two ends or open at one end and closed at the other. One interesting relationship is what's the difference between consecutive harmonics? So what's the frequency difference, say, between the fifth and sixth harmonics, or between the third and fourth, or between the 100th and 101st? That's a really interesting piece of information. So let's write down what that is. Let's see if we can find a relationship for it. So what is delta F? The difference in frequency between some mode and the one behind it. So say the sixth frequency minus the fifth. So n equals 6, n minus 1 would be 5. Or between the 10th and the ninth. What's the difference between those two frequencies? Well, Fn is equal to n times v over 2L. The frequency of the n minus 1 harmonic would be n minus 1 times v over 2L. Okay, now we'll do a little distributive property. Nv over 2L minus Nv over 2L minus v over 2L gives us plus v over 2L, which we notice is equal to the fundamental. So if tubes are closed at both ends, closed, closed, and for that matter, if they're open at both ends, we know that the change in frequencies between any two consecutive harmonics is equal to the fundamental. This is going to come up in a few of our examples. So next we'll talk only very briefly about tubes which are open at both ends. I'm going to invite you to go through the math of finding the wavelength and the frequencies on your own, but I'll talk about the boundary conditions at the open end. So let's think about what happens at an open end of a tube, so a water bottle with no top on it. So if we think about pressure, the air pressure at the very open end of a tube has got to be equal to the pressure in the outside air, so it's at equilibrium. That makes it a pressure node. Remember, node means the pressure is at equilibrium. So that's the boundary condition in pressure. If you have an open end, the air pressure at the open end is the same as the surrounding environment, so that's a pressure node. What about displacement? Well, at the open end, the molecules are free to move in and out of that tube. They can move all they want. That means they have maximum motion, so we have a displacement antinode. So those are our boundary conditions at the open ends. Now you can go ahead and you can work through the wavelengths and the frequencies. I'll post the answers, but I won't include it in the video. You'll see it turns out to be the same as tubes closed at both ends. Okay, so now let's look at the combination case. What if we have a tube that's closed at one end and open at the other end? So let's establish what our boundary conditions are. At the closed end, we have a pressure antinode because those air molecules get squished up right at the end. There's high pressure, or it's really spread out for low pressure. And the molecules can't move, so it's a displacement node. At our open end, there's a pressure node because all of the air molecules at the open end are in equilibrium with the atmosphere surrounding it. And there's a displacement antinode because those air molecules can move as much as they wish. So let's go through the process and let's first draw our pressure waves. So I've got a tube of length L and I'm going to draw the pressure waves. At my closed end, I'm going to have a pressure antinode. At my open end, I'm going to have a pressure node. Okay, so I'm going crest to equilibrium. So what fraction of a wavelength is this? This one can be a little bit tricky for people. If we draw one whole wavelength, so from an equilibrium to a crest to an equilibrium to a trough, we see that the fraction of the wave I just drew in the tube goes from a crest to an equilibrium. We have a quarter of a wavelength in this tube. So 1/4 of the first wavelength equals the length of the tube, lambda equals 4L. Okay, what about our next image? Well, our next pressure wave will have an antinode at the closed end and a node at the open end, but we need to squeeze in another node and antinode. So that's going to look something like this. Again, your book has pictures with really nice drawings. My picture's not so much. All right, what fraction of a wave is this? Well, this one, we go from a trough to equilibrium to crest back to equilibrium. So we have a half a wavelength and then another quarter. This is 3/4 of a wavelength. So lambda equals 4L over 3. Okay, next one. I've got my antinode at the closed end, got my node at the open end, and now I need to have two nodes in there with antinodes between the nodes. So now my picture looks like this. This is not too bad. So how much of a wave is this? I've got one full wavelength right here, and I've got another quarter of a wavelength right here. So in this picture, I have 1 1/4 lambda, or 5 over 4 lambda equals L, which means lambda equals 4L over 5. Now, this is an interesting development. This is similar, but different from what we had previously. I've got 4L divided by 1, then I've got 4L over 3, and then I've got 4L over 5. So I've got 4L divided by an integer, but those integers are only odd integers. Okay, that's interesting. All right, let's write down the frequencies. So my first frequency I have is V over that first wavelength. So V over 4L for my very first frequency. For my next one, I've got V over the next lambda. So I've got V over 4L over 3 gives me 3V over 4L. And then my next one, F equals V over the next wavelength. So V over 4L over 5 gives me 5V over 4L. My very first wave, again, is called the fundamental, and the rest are the normal modes or the resonances or the harmonics. Okay, now with our harmonics, they're different from if we had tubes closed at both ends or open at both ends. Let's start by writing down the equation. So if I have tubes that are open at one end and closed at the other, generally I just call that open-closed. What I see is that lambda n is equal to 4L over n, but n is only the odd numbers. And f, n, so I'll label this one as 3 and this one as 5, fn is equal to n times v over 4L. V over 4L is the fundamental, so Fn can also be written as n times F1. And n is equal to 1, 3, whoops, I said 3 and I wrote 5. 1, 3, 5, and so on. Only the odd numbers, but they're still called harmonic numbers. So in these tubes, we only ever have the odd harmonics. That's pretty interesting. Okay, let's go ahead and draw our displacement pictures. So at our closed end, we have the node. The open end, we have the antinode. So we go from node to antinode. Again, we have a quarter lambda equals the length. Our next picture, we have to squeeze in another node. So our next picture looks like this. We have 3/4 of a wavelength equals L. Last one's a bit harder to draw. So I've got my antinode at the open end because the molecules can move, my node at the closed end because they can't move, and then got my other nodes in there. And again, I have 1 1/4 lambda equals L. Again, displacement picture is this describing the same wave, just a different aspect of it, so we get the same relationships. The last thing we'll do now on this slide is ask, what about delta F? What's the difference between consecutive harmonics? So delta F is going to be Fn, take away the previous harmonic, but now we only have the odd ones. So this is, for example, say the difference between the 5th and the 3rd, or the 9th and the 7th. So it's not Fn minus 1, it's n minus 2, because the n's are different by 2. So I've got n times v over 4L, take away n minus 2, v over 4L, equals nv over 4L minus nv over 4L. Minus a minus gives us a plus, 2v over 4L. Those guys cancel, and I'm left with 2 times v over 4L, which is twice the fundamental. Okay, that's different from what we had before. So if we have tubes open at one end or closed at the other, we see that delta F is twice the fundamental. This gives us a tool that if we can measure the frequencies, we can sort out the nature of our tube.